Okay, so first of all, I'm very much thankful to the organizer and Bhaktishu Publishing Group for having me here. And I am Nida Izhar Mallick, a research scholar at the Department of Mathematics, Jamia Millia Islamia, New Delhi, India. And here the title goes a simple and efficient iterative scheme for image restoration. So in this presentation, I'll be presenting a new simple but very efficient iterative scheme to approximate the fixed points of non-expansive mapping. Also, I'll be showing its real-world application in image restoration by formulating the set problem as a split feasibility problem. So this presentation includes a brief introduction, some preliminary results, main results showing the weak and strong convergence of our proposed iteration, a numerical example in support, its corresponding graph, and application and references. So let's briefly understand what a split feasibility problem is, how it came into existence and then evolved into a problem that is now known as a split feasibility problem. So in 1937, Stephen Kegmars presented an iterative projection method defined by equation number 1 to solve a system of linear equation of the form Ax is equals to b, where A belongs to Rm cross n and b belongs to Rm. So what Kagmar geometrically noticed was that instead of solving all the equation at once to find a solution which satisfies them all, we can proceed by projecting the current estimate onto the solution hyperplane of each equation one by one. Like for example, if we take an initial guess and then project it onto the first hyperplane L1 corresponding to equation number 1 and then obtain a solution corresponding to it, then project into a next hyperplane and so on, continuing this way. So in this way, the point keeps bouncing between hyperplanes, getting closer and closer to the intersection. Then in 1957, Motzkin and Schoenberg presented relaxation method defined by equation number 2. Here, instead of simply projecting onto the hyperplanes, we move partially towards the projection using a parameter lambda which belongs to 0, 2 interval, open at 0 interval. By this method, but this method was only algorithmic and intuitive, and still it needs some stronger theoretical guarantees. So in the same year, after a few months, there came Eggman, who used orthogonal projection, especially when the case for lambda strictly equals to 1. The same method, but it took the lambda strictly equals to 1 and provided the first rigorous convergence proof for projection technique applied to convex set. So this way the foundation for projection method were understood. Then the further curiosity led to the generalization of this problem to from hyperplanes to the convex set. So in 1967, Gubin and Polyak generalized projection method to the problem of finding a common point of many convex sets defined by equation number 3. This method looks very similar to the idea of Motzkin and Schoenberg and given by Eggman. So this is the first time that the convex feasibility was formalized as a distinct problem class, and the definition they provided was this: to find a point in the non-empty intersection of finitely many closed and convex sets Ci, where I1 equals to M, for all where Ci's are closed and convex subset of Hilbert spaces H. Then onwards, convex feasibility problem became an important class which can be used to solve many real-world problems. And the traditional method to solve convex feasibility problem was that of orthogonal projection. Then in 1997, Sensen and Elfing extended this classical projection method by using Bregman distance-based projection, which are defined by equation number 4 and 5. And they also use many different kind of generalized projection in a single iterative process. And in order to motivate this their approach, they introduce an application under the name of split feasibility problem. So this was the first time that a split feasibility problem got its proper name and definition. They defined in their research article a split feasibility problem as for any two Hilbert spaces H1 and H2, let C be a subset of, sorry, this should be H1. C should be a subset of H1 and Q is a subset of H2 be two non-empty convex and closed subsets, and let there be a linear and bounded operator B from H1 and H2. Then the mathematical representation of SFP is to locate a point S belong to C such that its mapping, its image under the mapping B should belongs to the set Q. So there came after its like invention of the split feasibility, after the proposal of split feasibility problem, there came many methods to solve the split feasibility problem, but the complexity with all those methods was that they involved matrix inverses at each step, which was a complex method to find. So in 2002, C. Baine proposed a CQ algorithm, which was much efficient than all other earlier known algorithms, and it doesn't even involve matrix inverses. So the C-bind defined the CQ algorithm, which is defined by equation number 7. Then there came other version of CQ algorithm such as KMCQ-like algorithm. So along with the invention, or you can see the generalization of this convex feasibility problem to split feasibility problem, there was also a mathematical field that was also emerging at that time, as known as a fixed point theory, and many iterative schemes were being proposed. So in 2000, Noor proposed a three-step iterative scheme to approximate the solution of variation inclusion in Hilbert spaces, and after that it became very prominent approach for solving the SFP because it was much efficient and reliable than its earlier known iterative schemes such as Ishikawa, which was a two-step iterative scheme, and Mann and Picard, which were for one-step iterative scheme. And then in 2012, Dang introduced No's three-step method to the KMCQ-like algorithm. Further, in 2019, Feng merged Bayes CQ algorithm with Miai's three-step iterative scheme to solve the SFP. So, motivated by the research going in this direction, we propose a new simple iterative scheme defined by equation number 8. So here we took W, a subspace of a Banach space Z, and KW to W be a mapping for a given S1 belongs to W, and zeta and eta n contained in closed interval a comma b for some a comma b with a and b lying between 0 and 1. The equation is defined as equation number 8. This equation looks very similar to that of Ishikawa iterative scheme, but here is a pictorial representation showing that our iterative scheme is less complex than Ishikawa iteration. So I hope you can understand that if we take any point x1 here and then we find an image t of x1. Similarly, we did for iteration, then we find y1 and it's mapping here t of y1, which is done in Ishikawa iteration, but there is no such complexity here. We can directly calculate the next point. And this is the representation showing that our proposed iteration is faster than Ishikawa iteration. We took same mapping here, 1 minus x, and these are the fixed points. So here you can see the Ishikawa iteration is taking more steps to converge to the fixed point, but our iteration is converged to the fixed point at third step, sorry. Now comes the preliminary section. Here I included some basic results or definition that I used in my main result showing the weak and strong convergences. So here comes the main result section. First of all, we show the existence for this limit. Then we show that it is equals to 0. And further we proved the weak convergence of the proposed iteration to the fixed point of the corresponding mapping, and then we show the strong convergence of our proposed iteration to the fixed point of the corresponding mapping, non-expansive mapping. And then we proved the strong convergence for a mapping satisfying condition I. Here's a numerical example, a very simple example I took, which is of the non-expansive mapping, and corresponding to it, I applied MATLAB coding corresponding to various other different iterative scheme and found out that our iterative scheme converges faster than Man, Ishikawa, and Noor iteration. Here it is also clear that our iteration converges to the fixed point at third iteration, while others taking more number of steps. Now, as the convergence of our proposed iteration is developed, or so here I am showing that our iteration is not just of theoretical use, but it can also be applied to a real world problem of image restoration. To apply it to the real world problem, I first formulated the image restoration problem as a split feasibility problem. So for that, I converted the mathematical representation of image restoration is defined by equation number 11, where small b is the vector representation of the degraded image, and the small w is the vector representation of the original image or a true image, and m is the operator applied to degrade the original image. Then here, if I explain it, so you can clearly see there are two constraints. One is that the point should belong to the image space, and second is that after applying the degradation through the operator m, the point must belong to the measurement space. So this way, this problem is converted to a split feasibility problem, that one point should belong to a set C and the other point, then its image point should be in the set Q. And then we merge. Okay, then there came a very important lemma that was proposed by Feng, and that says that if a operator K is defined as a CQ-like algorithm, this step is taken from the CQ algorithm. So if operator is defined like this, then this operator is a non-expansive mapping, given this condition on the gamma. So this way, since the operator is non-expansive and the solution set, if we see the solution set for the split feasibility problem, this is the split feasibility problem, and the solution set defined as a common point that belongs to both these sets. So we applied this, and we can clearly see from here that a point is the solution of the SFP, split feasibility problem, if and only if the following fixed point equation holds. This is the mapping. So K of S is equals to S. So we applied that mapping K that was defined by the Feng to our iterative scheme, and then modified our iterative scheme as this, given by equation number 12. And then we use this mapping in our MATLAB coding to restore the image. And for that purpose, we took this original RGB image with the matrix size 488 by 504. This is the central gate of our university, which I took as an example. And we applied three different type of blur matrices. First one is Gaussian blur of filter size 9 by 9 with a standard deviation sigma 0 to 4. Second one is out of focus blur. Third one is motion blur. So we applied all these blur matrices as an operator to degrade the original image, and we obtained the degraded image as this. This one is corresponding to Gaussian blur. This one is corresponding to out of focus blur, and this one is corresponding to motion blur. So these are the these are the degraded images, and now we apply our iterative scheme to restore these images closer to the original image. So here we apply this. These are the restored images, This one is at 50th iteration, this is at 1000th iteration, and this is at 20,000th iteration, corresponding to Gaussian blur matrix. So if you can clearly see, there is a slightly closeness to the original image. Here is the image is more blurred, then a little bit clear, and a more clear. Then these are the restored images at 50th, 1000th, and 20,000 iteration, corresponding to out of focus blur. And these are the images corresponding to the motion blur obtained at 50th, 1000, and 20,000 iteration as well. Here is a pictorial representation I also created, sorry, a video representation I also created. I hope you all are able to see it. So this is the original image and this is a blurred image. I took just one example corresponding to Gaussian blur. And here you can see as the iterative step is increasing, so the image is getting closer to the original image. So for convenience, I can increase the step here. So yes, here the image is getting closer to the original image, showing the convergence of the points to the original points. Further, if I increase it, so at 9,000, it is getting much more closer to the original image. So yes, this was just then here the metric I used to measure the quality and the convergence or closeness to the image, real original image. The first one is the PSNR, which is used to check the quality, how good is the quality of the restored image corresponding to the Gaussian, out of focus, and motion blur. So these values are, you can see, ranging between 30, above more than 30. So the PSNR value ranging between 30 to 40 are considered to be a good value. That is, the quality of the obtained restored images is in a good category. Then here is a Cauchy error graph, again corresponding to three different blurry matrices. The Cauchy error is showing that how good our algorithm is converging to the fixed point, and the relative image error corresponding to the three different blur matrices, showing that how close our iteration is getting to the original image. These are the references, and this is all from my side.